Thanks for the introduction. I'm talking about Geodata and open source. I especially wrote open source modules because there are some non-open source modules doing the same, so we do the open source way. You see some fancy 3D pictures on the first slide. I have to disappoint you today. We stay 2D. It will be a very basic introduction to processing geodata. But what exactly is geodata? It's quite simple. There are some standards, ISO, TC 211, etc. But the most important thing is it has association with a location on the Earth. Okay, you could say on other planet too, but let's stay on the Earth today. And there are many different geographic information systems available today. I want to highlight two. One is ArcGIS of Esri, and the second is QGIS. Both can be extended using Python. However, I will not talk about geographic information systems today. I want to show you how to process geodata using Python in a Jupyter notebook. The difference is quite simple. In a geographic information system, you do capturing, you do storing, manipulating, analyzing data, manage and present it. In the Jupyter notebook, you can do exactly the same, but I want to focus today on the manipulating and analyzing part and a little bit visualizing part. So what do we have today for modules? There are tons of modules available. But two open source libraries. I say libraries because it's non-Python. Two most important libraries written in C++ are GDAL, and the second is GEOS. GDAL is the geospatial data abstraction library. It's almost 20 years old now, and it can do two things very good. It reads raster data, that actually images. And GEOS is the geometry engine open source. It's also written in C++. Actually, it's a port of a Java engine called Java Topology Suite, and it's being ported to C++. So GDAL does have a Python binding, but it's really, it's C. Basically, you have functions, and it's not Python. What we love here. So there were recently some nice Pythonic libraries being introduced. One is Rasterio. It reads raster data, and the other one was Fiona for vector data. But before I come to the libraries, I want to show you what exactly GDAL does. A little bit small, but I can make it bigger. This is the official page of GDAL, the C++ library with the Python bindings. And you see here there are some 155 different raster formats supported and 95 vector formats. And if you open the list, you see there are tons of these raster formats. Some you may know a little bit. For example, GeoTIFF. TIFF is a image format, but it can be extended for geodata. So you have certain information in there to position the image at the correct position. And same for vector formats. There are tons of vector formats available. Maybe you heard of KML or other ones, and you see there are really tons. And this library can abstract them all, and you can read them. And with Rasterio, which was created by Mapbox, you have a Pythonic way to access all these kinds of format. And then we have Shapely, which is based on the GEOS, on the geometry engine open source. And from these libraries and some more, like NumPy, etc., there is a library called GeoPandas. I'm sure you know Pandas, and there is an extended version for Pandas for reading geodata. May I ask you, who of you already used GeoPandas? So quite Not a third, but maybe a fourth. Okay. So I want to. I don't want to stay with slides. I want to go to a Jupyter notebook. You can download it here. You can make a picture, or I will put it on Twitter later, or on the EP Your Python page. So what you need is to install all these modules. It's quite easy. Most are in Conda repository, and one you have to get from CondaForge volume. It should work with Python 3.6. I didn't try it on Windows recently. I know it works with 3.5 under Windows. So if you use Windows, maybe you have to switch to 3.5. It doesn't work yet with 3.7. Because I like f-strings, you have to adapt it a little bit if you want to bring it to 3.5. So let's go to the Jupyter notebook. So you go GitHub, download it, and then you get this one. I will zoom a little bit in. It's quite small. Can you read this? Yeah, I think it's okay behind. Okay. So again, okay, you can install these things, but I assume you already installed that when you open the Jupyter notebook. Oh, by the way, you really need a notebook. It doesn't work properly on the Jupyter Lab yet. At least on my machine, I had some problems with images. So let's look at what we get in Shapely. Shapely, based on GEOS, supports several formats, several geometries like points, line strings, linear rings, polygons, multi-line string and multi-point, multi-polygon. The difference is if you have a multi-point, you just have several points. So you have one abstraction for all of this. So let's build a polygon, for example. So I create a very simple polygon. Shapely geometry, import polygon. You could do the same with points, line strings, etc. But I decided to use a polygon. And then you give the coordinates in this list with tuples. And very important, the first and the last is the same coordinate because it is closed. So you have to specify that. And then we can do some operations, for example, area, length of the polygon, and you get this back. And one nice thing, if you are in Jupyter, you can just display it within the notebook. But this, I have to say, is just for debug purposes. You can also display it using Matplotlib and others, but it's just simple. Just give the result, and it will be displayed in Jupyter Notebook. So I create a second polygon. You also see the scale is not quite correct compared to these two. It's just, as I said, it's just a debug output. So we have two polygons, and then I could make, for example, a union of the polygons, and you see you have a new polygon output, and can display it, you can access the coordinates, etc. You could also do an intersection of both. Okay, that's a little bit strange, but if you look at it, it's the inside part of the polygon, so it's a triangle intersection. And then one very nice thing is a symmetric difference. You take the difference of the two polygons, and you get a new polygon back, which looks like this. So it's really quite advanced, this Shapely. Okay, and of course you can do things too. You can get from these results. It's a new polygon. You can get a length and error again. Okay. So you want maybe to see the output. There is a format called WKT. It's well-known text. It's actually a standard from the Open Geospatial Consortium, actually a part of a standard, but I'm not going into details here, where you can use text to represent all these shapes. So in case of this symmetric difference, you get back a multi-polygon because it's more than one polygon, and here are the coordinates. So the type, by the way, of this is just a string, so it's really serialized as a string. And you can also load again with this string. So if you type this polygon as string, or you have some file where you can import it, you can use wkt loads and load s for string, and you have the polygon back. So it's just a pretty easy way to dump and to restore a polygon from text. By the way, Shapely doesn't support many formats, actually just the serializing formats. You can also use GeoJSON with some tricks, but basically the best way is using these well-known text representations. There are also some very interesting binary operations available. You can check if a point, for example, is within a polygon, or you can check if a polygon is within a polygon. You can check, does it intersect, does it cross, is it equal, does it touch, and so on. So it just gives back true or false. So say polygon 1 intersects polygon 2, or polygon 2 intersects polygon 1, is the same. In this case, yes, they intersect. And is it within? No, it's not within. And is it equal? Is polygon 1 equal to polygon 1? Yes, of course, it's equal. So you can just do these kind of tests. So I'm leaving Shapely for now. We will come back to that in a later. Let's go to Fiona. Fiona, as I said before in the graphic, is based on the GDAL library. And it can do more than just do operations. It can read formats. So we saw this almost 100 vector formats before. We can load from this quite easy. You just import Fiona, open the data file. I used Esri shapefile. It's a very popular format for vector data. I read it. I could also write a new one, and then we can iterate through these data sets. Let's just look at the first. With next, I can access I iterate through the whole data set. So with next, I always get the next one. So the first data set in this is it's an airport data set. From Natural Earth, they have a public domain shapefile with all, or most or many airports in the world. And here the first airport in this is based in India. And you see there are many attributes together. So we don't only have the position. In this case, we have a point, like we had a polygon before. Now we have a point. And we have its coordinates. This is the coordinate of the airport. It's WGS 84. We come to that shortly, and it's a geographic coordinate. So it's an airport. It's a small airport. The name is Saneval or whatever it's pronounced. There is abbreviation. There's a IATA code. This one you know if you book. Anyone know the code of Edinburgh? EDI. EDI. Okay. Yeah. We come to that shortly, and you see you can just access it. It's basically a dictionary. So you can access these attributes, properties by using the standard way to access dictionaries. So we have actually two ways to open this airport. One is creating a list of this collection. You see this after open, just create a list, and you get a list of all airports. The big problem of that is if you have a huge data set, you will run out of memory. So the second way, we already did that, is just iterate through it by using for loop. So I use the with, so I don't have to close the data set airport shape as C like collection, and then I loop through airport in this collection, and then I check if properties IATA code is Edinburgh, and if it is Edinburgh, okay, print the name, coordinates, and the Wikipedia link. Yeah, the Wikipedia link is also stored in this data set. So I run this, see, it was quite fast. You get the coordinate, Edinburgh International Airport. You could go to the Wikipedia page and look exactly for more information there. So we saw coordinate, but you know the Earth is not flat, unfortunately. It would be much easier. So we have coordinates, different coordinate systems on the planet. Actually, every country has at least one coordinate system. But for this dataset, a global reference system is used, the WGS84. You can check what reference system is used by coordinate reference system. So collection.crs, coordinate reference system. You get EPSG 4326, and EPSG stands for European Petroleum Survey Group. They created numbers for every coordinate system, and the 4326 is the WGS 84. You can check it here. It's a nice web page, epsgi.io, and you can just slash the number, and you get the information. So it's the WGS World Geodetic System 1984 used in GPS. So, and you see the coverage, it's the whole planet. I'm not going into details with projection systems today due to time restrictions of this talk. Oh, I'm already behind schedule. So if you are interested, you can check out PyProj, so you can transform from one coordinate system to the other. So let's do something. We open, again, a dataset, a different dataset. It's the admin 0 countries shapefile from Natural Earth. Admin 0 means it has all countries of the world. But for example, admin 0 means we only have Great Britain. We don't have Scotland, England separated, so it's admin 0 country. So we can see the first, again, you see, this time we have a multi-polygon for every country in this data set. So we can also access, again, some information, for example, the name. The name is also available in different languages. You can check the continent. You can check out what's the population, year. And again, I do a loop through all elements in this collection and check if the name is United Kingdom, and then I just print these things. Okay, population for 2017, and it's a multi-polygon. So let's do a quick example. We have two data sets now. We have the airport data set and this country data set, admin 0 data set. So what we can do is we can say, okay, give me all airports within this UK polygon. So it's quite amazing. It's just this. Okay, first we check out if this is the UK, I think. Yeah, it looks correct. And you see, just get this, before we stored it, by the way, I stored the geometry from this data set, so I have it here. So I have to create the shape of this geometry, and I can look at it. This is basically the same like the Shapley polygon. It is actually a Shapley polygon, so we can interact with Fiona and Shapley. So in this short code sequence, I open the airport files, iterate through all airports, and check if the position of this airport is within UK, then it prints. And you see, it's quite fast. We can output it. You may see there are not all airports here. This is because the data set is not really complete. So that's the problem of the data set, not of the algorithm. But I don't think in another language you could do this in 1, 2, 3, 4, 5, okay, with the import 6 lines of code. So it's really amazing. Okay, let's quickly go to Rasterium. It's for raster data. So you have an image file, for example, GeoTIFF. You open a data set, you have many parameters. Basically, you only need 2. If you start, you can say, I want to read it, and I want to open the file name. So it looks like this. I used the Blue Marble dataset of NASA. It's the whole planet inside. And this is already all just open. And then I can access all attributes, name, okay, as you know, the mode. We read it, count how many raster bands you have. You have RGB in this dataset. So we have 3 raster bands. And I can also do it with the indices, so 1, 2, 3 are the indices to access them. I can have the width and height of the file. I can look at the coordinate reference system. Again, it's EPSG 4326, so it's WGS 84. And then we have something very special. We have the affine transformation. So it's basically a matrix. You can have pixel coordinates and transform them to the coordinate reference system. So, for example, if you transform 0, 0, that's the top left of the image, it has the coordinate of minus 180 and 90 degree. So it's geographic coordinates. You can also do the inverse affine transformation, just with the tilde in front of the affine, so you get this transformation. And if I transform the 0, 0, that's the middle of the image, basically middle in geographic reference system. So I get pixels 1,800, 900. Now we see we can compare it to the width and height, which is in this dimension, so it's in the middle of the picture. So, okay. We could also see where is the Edinburgh International Conference Center located in pixel coordinates. So I take the geographic coordinate of here and print my pixels, and you see this pixel represents this conference center. So we can also see the bounds, where it is located. That's not very special. What I want to do now is read the RGB data and display it using matplotlib. So what I do is I want to read it in a NumPy array. So we saw there are 3 bands, red, green, and blue, and I have to read them separately. This is because images can have more than 3 bands, spectral images, for example, or elevation files with only 1 band. But now we have a RGB, so it's quite easy. So with dstack, I can put it in a representation where I only have RGB together. That's the easiest way, and then I can just plot it using matplotlib. And we see this takes a while. It's a big image. Yeah, okay. That's the red dot would be in this position. So it seems to be correct if you look at it. Yeah, okay. So let's go to GeoPandas. Still have time, I see, more or less. Yeah. So GeoPandas combines all this. But why, maybe you ask yourself why I showed you this Shapely and all these things. The problem of pandas and GeoPandas is if you really have huge data sets which don't fit into the memory, you have to use this without pandas or GeoPandas. And if you have geographic data, sometimes you have terabytes of data, so you can't really have everything in RAM. So first we open a data set. It's a CSV file. I use pandas for that. It contains all cities with a bigger population than 5,000. In UTF-8, it's comma separated. Its origin is geonames. It's also an open data set. And we see the first 5. We have the name of the city. We have the name in Latin, one, so without special signs, and then we have the name of the city in different languages, the geographic position, other interesting information, where it is, time zone, and so on, when the data set was created. So you see that's a normal pandas output. And first, what I do is I want to reduce it. We are not interested in all information. So I take the columns 1, 4, 5, 14 and give them some names. So now it's quite easier to see that. I take the name in UTF-8 and latitude, longitude, and population. So that's the whole data set now. And let's do a query just to see if everything is correct. Edinburgh is within this data set, and we have latitude, longitude, position, population. I'm not sure if it is correct, 464,990, probably. So let's switch to GeoPandas. Actually, the difference, if you have this, the main difference of GeoPandas is you have a column called geometry. And in this geometry column, there's the geometric information, actually as shapely, stored as shapely polygon or whatever. And we can just take this data and convert it. We create a geodata frame, and for every, we create a point of this position, longitude, latitude, and zip it together, so we have actually a shapely point in this geometry data frame. So a geodata frame has a column geometry, and this consists of these shapely points. So let's look at it. We see it's basically the same. We just have a geometry column, and that's basically all. So we have a GeoPandas data frame. So I drop, you can leave it inside the latitude, longitude, but I drop it, and you see, actually I could display it again quickly. GDF head. You see it's without latitude, longitude, it's redundant, so we have the geometry here, so it's the same. So what we can do, we can just call geodata frame plot, and we see a matplot output. I should use semicolon, and this is all cities on the world. You see, I think you can imagine the continents. There are no big cities in the water, so yeah. So we can export that dataset to a shapefile, for example. Just GDF to file, take the driver shapefile. You could also export it as GeoJSON and some other formats. And very important, encoding, UTF-8, especially if you use Windows. And then you see in your file system, this takes a while, a shapefile with this. Okay, so this really takes a while if you don't have power. And you would see in the Explorer, yeah, I'm not showing it due to time. You will see the city's shape is inside. You could open it with QGIS, for example, or another software. So I store this geodata frame. I call it cities, just to remember cities. That's my dataset. Just for later, keep it. And we can do some queries on this cities dataset. Let me create a new geodata frame called big cities. Just I want all cities with population greater than 10 million. And yeah, it's this one. You see, it's not 100% correct. Here it says Shanghai has the biggest population. It's just, again, this data set has these numbers. And we see the 10 biggest data set. I sorted it ascending. It's correct. And okay, let's load again this data file. We take GeoPandas and read file, and we load these countries, admin 0 countries we used before in Shapely, Fiona, sorry. And then we look at the data. You see, I can actually open this shapefile, and I have a GeoPandas output. Again, it's a little bit too big. I just want to reduce it to the name, the population, and the polygon. We can also plot it again. I'm not doing it, just call plot, and you see the whole world. What I want to do now is I want to, again, take United Kingdom. Now with the GeoPandas or pandas notation, I look for countries, name, United Kingdom, and we see this result. And now let's plot it. This will use matplotlib, and we see, yeah, that's the result. You also see it's not high resolution. It's on GitHub. I used the reduced version of the polygons, so we don't have to download many hours. So let's make another query. I make the query rest of the world, and say all countries where the name is not United Kingdom, and I plot both together. I make this axis plot, save this plot with color red, UK, and then use the rest of the world plot, give this axis back, and displayed blue. So you see it actually works. You can have several data sets like this together. You could have 100 different data sets and plot it. You can try it yourself. You can take the country you're from or your favorite country or whatever and color it in your favorite color. And now we see we can actually access this shapely. You have to use the iLock 0 and access the geometry, and you actually can access the shapely polygon from within pandas. And now you can also do some with that information, you can check if a city is within. So I take this cities data, remember I stored it, GeoPanda cities, it's all cities with population greater than 5,000, and I say I would like to have all cities within this UK geometry, and let's plot the first, let's display the first 5. You see this takes a while, so it checks, it goes through all these cities, and you see UK cities, it's all cities within UK in this geometry position. Okay, so now let's go to the last interesting module I want to show today. It's volume. It's, maybe you know Leaflet.js is a mapping library. It's also used for OpenStreetMap. If you open OpenStreetMap, you see this map, and it's based on Leaflet. And volume is a Python version accessing this Leaflet.js. So what you can do is import volume. You can have a map, location, the center of the map. I use the Edinburgh Conference Center and say zoom level 17, and what it creates is just a map. Yes, the internet is working, great, and you see center of the map is our conference center, and you can also save this map, we'll see it later. It's really, in 3 lines of code you have a map, so it's really easy. So the interesting thing is you can combine GeoPandas and volume. So again, we have this UK polygon, and now what you can do, we have volume. In volume we have a function GeoJSON, and in this function you just give the GeoPandas data frame and add it to this map. So if we do that, we see our nice polygon is now on this map. So maybe you tried that with the original JavaScript library. It's possible too, but it's double number of lines. So it's really very easy to add this polygon. And now you want to say maybe I want to color it differently, every country in a different color or something. That's also very Pythonic here. You just use GeoJSON, and you can give a lambda function or whatever function where you take the feature and you can access this feature. You can say fill color. You could also make a function here and use the feature again, but I don't want to have too many lambda functions here, so I keep it easy. And I just say green, but if you have a function, you can say if this feature is country whatever, then color it green or blue or black, whatever. And so this can be a function too. Everything here can be a function too. And add it again to the map, and you see I make green, fill color green, and outline color black, a dash array, and you see it looks like this. So next is, okay, you want to have, you remember the big cities, this 10 largest cities in the world. So what you can do with volume, you can create a marker and also iterate through all these with the apply function of GeoPandas. You take every data set and you create a marker. You can access the data, so I just do it now. And you see the 10 biggest cities are on the map. You can, of course, combine everything. You can have markers, you can have polygons, and at the end, you can just say, save the map, my map, HTML, and it should be here somewhere. develop, yeah. EuroPython should be here. Yeah, and this HTML should be located. Oh yes, my map HTML. So I open web browser, and this is the result. So this is just one HTML page with our created map. I could do the same with the UK polygon. So you can really create HTML of your map, and you could also alter this HTML and extend it using JavaScript. Okay, that's basically is what I wanted to say. One more thing. If you are interested in Geodata and Python, I'm organizing next year the GeoPython conference again. And since yesterday, I know the date. It's from June 24 to June 26, 2019, in Basel, Switzerland, in a brand new building. Our campus has a new building. It will be finished end of this month, hopefully. And actually, people are already moving in, and the restaurant is already open in there, and the first 5 floors are ready, and we are moving in the middle of August. And but about the conference, it's about Python and Geodata basically, but we enhance it for computer vision, remote sensing, and image processing, machine learning, and much more. And it's really easy to access with public transport. We even have our own train since this year. Okay, so it's time for questions. Thank you very much.
Thanks very much. Does anyone have any questions? Down here first.
I'm very excited to see all the manipulations on the shapefiles. It's very exciting, and you can do all those heavy lifting easily. I'm very much interested in this topic. Can you recommend some books which can get in your world, in data processing world, to get some pinpoints so that we are not just as an engineer popping getting down.
Yeah. There are really some books about this topic. Geoprocessing, it's from Pact Publishing, but books, it's nice to have books, but the problem is this is evolving this rapidly. So in 2 months there are new features. So it's really difficult. I think that the big time of books is I don't want to say over, but it's you know what I mean. It's just the best resource is still online. Check the repositories. I made links of everything, and they often have examples. For example, Folium, they have tons of examples with some marker clusters and everything you need. So I would look there first. And if you really want a book, you can find it from Pact Publishing, for example. They have geoprocessing. There are other ones. Just Google. Manning has one geoprocessing book. I have it too. But it's already 1 year old or 2 years old, and it's just not up to date. That's the big issue.
Hi. Thanks for the talk, Martin. Very interesting. By the way, I was in GeoPython in Basel in 2016, and it was awesome. So I recommend everybody. It's a very good conference. So my question is about the test. Also, the type of format test is WKT, I think you said. If you can talk a little more about it, if it's compact and is becoming a standard, or is a good GeoJSON alternative to get geographical information in a compact way.
You mean the file format of Geodata?
Yeah, there was a...
Okay, there are several. You saw, for example, this WK, the well-known text. It's ASCII, yes. Of course, it's huge. You can't really store that. There's also a well-known binary, which shortens it. I didn't go into that. And then, of course, there are tons of vector formats with compression and without compression. ASCII is still very popular in the geo world, even for for raster data because it's easy to interchange. But your question was the most compact format, or?
I was wondering if I didn't hear about that format before, so I was wondering if it
Shapefile,
was
you mean shapefile format?
well-known test.
Okay, so Esri shapefile is quite common in the geo industry. It's a very old format. They support UTF-8 too and many things. So it's a very popular format. That's
I was wondering for the well-known test.
the well-known text, yeah. Oh, okay. This one is from OGC, the Open Geospatial Consortium. It's part of another standard, OpenGIS. The best way is you Google it or you go to Wikipedia, well-known text. There you find tons of information about this format. It's very popular, this format. It's used for different things, also for coordinate reference systems or the definition of coordinate reference system. It's quite popular. But the big problem, the big issue is that it's ASCII and takes space.
Yeah.
And for that, use well-known binary.
There's a question down at the front.
Hi, thanks very much. I was wondering how well these libraries, for example, Raster.io, work with data where the geocoding is not in a fine transform, but for example, ground control points or type point grids. And also, what's your take on NetCDF and Xarray, for example, for multidimensional geodata?
So first, if you don't have georeference data, you have to do it yourself. It's clear. So you can add, for example, if you have a TIFF file, you just create ASCII file, TWF file, and then you specify that. And for the formats, as I said, there are tons of formats. I can't say this is the best format. If there would be a best format, there would be only one format. So I think that answers the problem. Every company has its own format for certain purposes, even if it's marketing. So we have more than 200 different raster formats. And if you look, for example, at the 3D formats, it's even worse. Every 3D software has its own format, so it's a big issue. The only way is GDAL is using abstraction layer, and if you have a new format, you just write this part of the abstraction and then you access it.
Thanks. Any other questions? No? Yeah, oh, sorry, yeah.
Just because, thank you for the talk, just because there's no more question, now I just wanted to say there is the GeoBuff format, which is based on protobuf for two-dimensional thing. I think the most compact format actually is from Mapbox, and it's GeoBuff.
Yeah. One more format, yeah. But it's nice, yeah. They say it's the most compact format, of course, and it's one more format. But I think it's good, yeah. Exactly. But the big problem is data delivery, who supports it now, and so on. It's not this easy, so you have to, especially if you access data, if you access GeoJSON from a service. There are many open data portals, they offer GeoJSON, so you have to use GeoJSON, you have no choice. Exactly, yeah. Exactly. Which is important, yeah. But I often see just gzip encoding from the web server using GeoJSON is very popular too. It solves some things too. It's not perfect, but it's a way to.
Sorry to interrupt with one more format. I'm just thinking of the talk by Peter Hoffman about Dask, Apache, and Parakeet, and it's very compatible with pandas. I just wondered if you knew if GeoPandas could extend to that, so that you didn't have to open very massive shapefiles, because I think it had a very clever thing for ordering and selecting by features and columns, so you could quickly access things.
GeoPandas is open source. Everyone here could write something. You could put a ticket on GitHub and then see what happens. That's all I can say. But thanks for the input.
Okay, thanks. I think we'll leave it there, and thank Martin again for his talk. Thanks.